Okay, so you pretty much gonna know what it's about because that's the practical implementation. So please welcome Andreas Vogt.
Yeah, thank you. I must apologize in advance. Defense is not sexy, it's not as nice as all the other talks about breaking things. It's boring, it's math, and well, if you enjoy it anyways, you're very welcome. So, certified programming with dependent types. I think most of my talk will be an introduction into what exactly dependent types are, because I think many people do not know. If you know Haskell, you can skip the first half of the talk and come back later. If you have experience with Cork, you can come back 5 minutes before the end. And for everybody else, which I assume is the majority in that room, I'm going through the motions very, very slowly. I've liberally stolen examples from the excellent book by Benjamin Pierce and colleagues. It's called Software Foundations. It diverts off on the way towards formal verification and program language semantics. That's I'm not going to deal with. I'm just using enough out of that to explain how data and proofs work in Coq, and then show how dependent types work in Coq and what you can do with it. I'd especially like to thank Marco Schöpel. He's the guy who wrote the software with me, and he's a brilliant mathematician, still learning how to write big applications, and for me it's the other way around. So we extend each other magnificently. What you see here is an Emacs running Proof General, and that's an interactive connection to Coq. Coq COQ is a so-called proof assistant. I can interactively execute statements here, and then they're highlighted blue in the top window, and in the bottom window you see the output we're getting. So that's comments. Okay, I'm going to start with the TLDR if you know everything else about Haskell and types. Dependent types are types that do reference back on code. So, for instance, you can talk about properties of some type of data. So, in a regular language, you can say x is an integer, well, the type is obviously integer. If you have dependent types, you can say x is an integer and x is even, or x is an integer and x is prime, or that list is sorted. So you can use arbitrary propositions that make up the type. So it consists of a base type and it consists of a proposition that's true for every element of the type. And you can do funky stuff with it, like making sure that if your function depends on some precondition, that the caller has to prove he meets the precondition, or that you can tell in your software that what you return is not just a list, but a sorted list. So that's a TLDR. And now for really starting with 0. So Coq, the tool I'm using, is a French proof assistant. It's written by a subgroup of the people that also did the OCaml stuff. It uses the calculus of inductive constructions for data types. It uses the lambda calculus for calculations. And it bootstraps everything else, the whole computational universe, as well as the whole mathematical universe out of that. Okay, I'm going to start with lambda calculus because that's something many people faintly remember. So most of the people who did computer science undergrad studies once heard about the Turing machine, and then they heard that the lambda calculus is equivalent to the Turing machine, not much more about it, which is a shame because, yes, it's computationally equivalent, but the proofs are 20 times easier than doing proofs in a Turing machine. So if you want to write certified software, meaning software where you can prove that it fulfills a certain property, it really helps if the proofs are kept short. So using the right mathematical foundation is important to make sure that the whole process is viable from an engineering point of view. You want to end up with a software and you want to have a proof. You want both to be manageable. Lambda calculus consists, well, colloquially speaking, if you say f of x, and normal mathematical notation. Equals x times x. Then we know if we want to calculate f of 3, we take the x and substitute it by 3. So lambda calculus is essentially function definition, function application, and using substitution for that. Like that, right? That intuitively is lambda calculus. You define functions, they have parameter gets substituted, end of story. Now for the calculus of inductive constructions. So lambda calculus works on some x's where things are in there that get substituted, and the logical question is what things? You have to be able to talk about the data you're computing on. That's where the calculus of inductive constructions comes into play, because it, as the name says, allows inductive definitions of new types. And with Coq, we're really starting in a vacuum. Nothing exists. Okay, you get a standard library, but I explain to you how central concepts are implemented in that standard library, so you get an idea of how programming that works. I open a temporary module to hide the standard definition library because we're going to start to define Booleans. Inductive is the keyword. It says we are defining an inductive definition here that gives the name bool. It's a set. We are defining a set bool. And we're giving two constructors here. One is called true, one is called false. And both constructors have the type bool. That means they're taking no arguments. I can do that definition. See, bool is defined. A couple of other stuff is defined that gets interesting later. I can use the check command to see the type of an expression. So I can write true, and if I say check true, I see colon bool. We're dealing with bool here. Same, of course, for false. Check only looks at the type of an expression. If I want to actually evaluate an expression, compute the result of an expression, I need to use eval. That's what I'm doing here. Okay, so yeah, we still need one other bit of the puzzle to finish being able to write anything we need, and that's writing functions. As I said, it's based on lambda calculus, so if I pass a b here, it gets substituted there. And the only thing that is added to the language beyond that is that match construct. You give it an expression here, and then you have a breakdown of possible values there, and then the results. If you have ever written Haskell or OCaml or something like that, that's totally obvious to you. The interesting difference towards Haskell and ML is that all functions are total, meaning it's defined for the whole range of arguments. And in such a match, every possible constructive type must be defined. So I cannot leave away the false branch in the match here. It always has to be complete. So if I look at that bool not, that of course also has a type. And the type in this case is bool arrow bool. So in other words, a function that takes a bool and returns a bool. I can also take the type of an application of that function. So if I pass true to bool not, that's an expression that has also type bool. So type was bool arrow bool, I pass a bool and bool remains. And of course I can compute the values. Bool not from false is true, bool not from true is false. I think that should be pretty obvious until there. There's a third way to actually do something like computations, and that is the example facility, which in fact states a theorem, and you can also use a theorem or lemma keyword, that doesn't matter, but I'm using example here because I use it as an example. I say my test bool not of true equals false, and then that happens. I see, that's the interactive proof editing mode of Coq, the proof assistant mode. What I'm seeing here, below that double dashed line is the goal I want to prove, and above that is the hypothesis I have. At the moment I do not have any. What I can do is simplify the expression, which applies the function essentially. Then using reflexivity as a, you talk about tactics, small tactics that get you closer to the proof. And reflexivity says something is true if both sides of the equal sign are equal. So I say that. And I said proof completed, and I can say QED. Yeah, I've shown that my example is always correct. Good. We will see more about that proof facility later and about how proofs are implemented, because that's really fascinating. That's where your mind starts blowing. That's the boring stuff, but I will tell that so you get the rest. That's another definition. This time we pass two variables. So again, definition, the keyword for the definition, name of the function. Parameter b1 is a bool, parameter b2 is a bool. The type of the definition, again, is bool. And the result type. And there again is a match that implements Boolean OR. I can check that, and again the type is bool, arrow, bool, which means I have to pass two Booleans to get out another Boolean. Or if I pass in one Boolean, it's also something people in static type languages are familiar with. If I pass in one Boolean, I'm getting back another function that takes a next Boolean and then returns a Boolean. Of course, I can evaluate that. I can check. So, okay, here's the case where I pass two arguments. I can evaluate that, get back a result. Okay, now stuff is getting more interesting because we have Booleans. Now we define natural numbers. Again, it's an inductive data type. And the peculiar thing about inductive data types is that it gives us a lot of information that we will need later when doing proofs for that code. Because in such an inductive definition, I know if I have an instance of a nut, of a natural number, I know that it had been either constructed using this constructor or that constructor. In that case, this looks like the definition of true in the Boolean. We have a constructor that's called O, and it directly returns an instance of nut. And then I have another constructor. Could you turn it off, please? We have another constructor, S, for successor, and that constructor has a type nut, arrow nut. So it's a function that takes a nut and returns a nut. That means there are two ways to construct a nut. Either I say O, and I call it my 0, or I can say successor of another number. Like O is a number, C, type nut here. Successor of O is a number. I could call that 1. The successor of O is also a number. You could call that 2. And in fact, we do see that a bit. And again, I can define functions working on that. That's the predecessor function. And I have a match here. I'm cheating because my function is total, so the predecessor of 0 is also 0. But for the other case, the n I pass here is destructed. I know it's the other case, it's not O, because O is that case. So there must have been an n prime that was used to generate my n. So matching with s n prime destructs the s n prime and can use the n prime on the right-hand side. So I pass a 1 here, which is s of 0. The n prime matches with a 0. I end up with a 0 and return a 0 here. And again, I can test that by computing the predecessor of 2. That is 1. Okay, I'm leaving my own world for a bit, go back to the standard library, because all that I've shown you is part of the standard library. And in fact, ordinary numbers, like the 4, are just syntactic sugar for successor of successor of successor of successor of 0. That's also 4. And I can compute successor of successor of successor of successor of 0. I'm getting 4. And I can compute successor of 4, getting 5. Okay. Natural numbers, yeah. Back to excursion mode, because we're defining more stuff that's in the standard library usually. Adding two numbers. Now that's a little bit more difficult because we need to have a recursive call in there. And what we have to do here is do a fixed point definition. That's why we have the fixed point keyword here, not the definition keyword. So I'm passing, it's again a function definition, with the difference that the name is bound in the body of the functions and can call it here recursively. I pass it an n and an m. Again, returns a nut. And I think how it works is obvious. If n is 0, the result is m. If n is 1, it matches here. So it's the successor of n prime plus m, and that eventually terminates when n prime hits 0 and gets passed here. So if I pass 2 and 3, it calls plus with 1 and 4, and then with 0 and 5, and then it returns 5. That's a very interesting message, because actually Coq is not Turing complete. I know you're all shocked. You cannot define a recursive function in Coq without giving proof that it terminates. So it's not, we circumvent the halting problem by just not looking at the part of the problem space where we cannot come up with a proof for termination. So either you have a proof of termination or you cannot write the function. That makes stuff sometimes a bit harder. You sometimes find bugs you wouldn't otherwise. And most importantly, if you could have functions that do not terminate, you could have vacuous proofs of infinite size that prove everything that breaks the proof part of it. But that's the technical aspects. Okay, but anyways, what you see here is that in that match, we destruct the n. We are taking s, n prime. And eventually, we match with a 0. And we have an inductive definition, so the compiler knows that there are only 2 ways to generate a natural number. That's 0 and successor. And it sees that this argument, n, is structurally decreasing in every recursive call on its own. So it says, recursively defined, decreasing on first argument. Sometimes it's not that easy, and then you might have to work hard. In that case, it's easy. Okay, we can do the computation here. Now that is nifty. You can actually extend the grammar of the language by adding grammar production rules to it while writing your program. So x plus y, you can come up with a notation for that. You say this is equal to that. Just like that, come up with your own mathematical notation, which is extremely useful. So 2 plus 3 is still 5. And then, of course, you can implement multiplication recursively by calling plus all of the time. And, you know, I said we are starting in an empty universe. You're not even getting equality for free. Well, actually, in the latest versions, you do. There's some auxiliary function that generates it. But you also can, and sometimes you have, to define your own notion of equality. So BEQ nut, that's a Boolean equal for the type nut. That's why the funky name. But that essentially tests whether 2 numbers are the same by, you know, taking, using structural recursion until both sides are 0. If they are both 0, they're the same. If they're not both 0, they're not the same. Okay. Yeah, I need that function later, so I'm going to show it to you now. You can also match on nested expressions here. That's one of the main reasons. We have a function even b. It takes a nut, returns a Boolean. That's why the b. And we're matching on either 0, that's true, or 1, that's false, or if it's the successor of some number, where the number is not 0, it could be 0, right, could be. It recursively calls itself. So now the funky part. You can take the code you have written like that and extract it into either Haskell code, which then looks like this, or you can extract it into OCaml code, which then looks like that. So the stuff I've been working on since the last talk is a PDF parser. I intended to write a PDF renderer, but turned out writing a PDF parser was enough of a problem. And the route we chose was actually writing the implementation in Coq, then extracting that to OCaml, using that to compile the binary. So that's a viable way. Essentially, we're using Haskell and OCaml as assembler here because all of the interesting stuff that I'm coming to in a moment, like having proofs about your code and passing around proofs, that gets extracted away, and that's not part of the executional model. Okay. So I can write programs, I can extract them to OCaml and compile that. Wonderful. Now for the proof part. You can, there are, I mentioned so-called tactics. I'm going to look into a couple of standard tactics that you use to solve, to prove stuff. Just to give you a rough idea, don't expect you to remember that or being able to actually use that, just to give you an idea of how that works. So I'm stating a theorem here. I'm giving that theorem a name, then a colon. And then here is the actual proposition I'm trying to prove. So I'm saying here for all n of type NOT, 0 plus n equals n. So that's our goal. The first tactic I use is called intros. That takes the for all from my proof goal and pulls it up into the assumptions. Then I can simplify the expressions, you have seen that before, and I can then use reflexivity, which you also have seen before, to show that it's true, QED. Actually, reflexivity calls simplification before, so I'm going to skip using reflexivity from now on. Okay, next example. I say if n equals m, then arrow is implication, n plus n equals m plus n. Which is kind of obvious, but unfortunately you have to prove even the obvious stuff. Or maybe fortunately, because you do not overlook stuff that you think is obviously correct when it isn't. So again, we're using, that's our proof goal. We're using intros to pull up the n and the m into the assumptions. We then use intros again to split up that implication, because that's an assumption if I want to show that. That's what the implication means. So I pull that up as well. And now I see I have an equality here, a hypothesis H, that n equals m. And I can use rewrite to actually rewrite the n for an m in there. That arrow says what direction to rewrite in. I say, ooh, the n changes to an m. Both sides are equal. I'm back to my reflexivity and QED. Sometimes proofs are a little harder. So that here, you've seen that above, is Boolean equality of a natural number, which is not the same as this one, right? That equality is a proposition. That's a logical equality. Whereas that is a function that, when it gets called, returns a Boolean. It's two completely separate concepts here. I'm coming back to that in a moment, so bear with me for a moment. So I'm saying this is an expression that returns a Boolean, and that expression is equal to false. And you'd think that any n plus 1 equals 0 should be true, shouldn't it? We can try solving it like we had before. We use intros to pull up the n. Then we try simplification, and bad, nothing happens. Okay, admitted, cancelled the proof. It says, okay, we cannot show that. Admit that. And try that again. Same theorem we want to show. Now this time, we're using a new tactic called destruct. We say here we know n is a natural number. So we have, in that inductive definition, exactly two ways of generating a natural number. Either it's 0, or it's the successor of some other thing. So we say we destruct the n, and look at the two cases. We look at the case 0, and that's the non-existing parameter here between the opening bracket and the pipe that doesn't get a name because it's not there. And in the other case, we have successor of something, and that something gets the name n prime in here. So we see there are two subgoals we want to prove. And now that we can simplify and prove by reflexivity quite easily. So that's my first subgoal. We show that it's true for a 0 case. It is trivially. And we show that that is true, and we're done. Okay, now for the fun part. Since we have inductive definitions, you probably already have figured that we're going to do inductive proofs as well. And that's what you do. That's where the fun starts. So again, we try to show something that's pretty obvious, n plus 0 equals n. Now, in the other case around that we had above, where we had 0 plus n, now it's scrolled out, okay. 0 plus n was easily simplified. N plus 0 isn't as easily simplified because it's not left recursive. So we try what we did before, and it doesn't simplify. Dang. Okay. We try the trick we learned before, destruction. We look at the two cases. Intro is n, we destruct n. We have the case n equals 0. That's looking pretty good. We can simplify that and say reflexivity. But now we want to show that, and it simplifies, but we cannot really go on from there, can we? We have now, there's something missing. And the thing that is missing is called the induction hypothesis. And that's what we're going to do here. Fortunately, if we do an inductive type definition of some type in Coq, we'll automatically get a theorem that gives us the induction principle for that type. And that we can use using the tactic induction. Okay, intro again, this time the induction. 0 case as before, trivial. And now the second case, and we have an induction hypothesis, IH induction hypothesis for n prime. We simplify. We see we can use the induction hypothesis for rewriting our proof goal. Both sides are equal, and we win. Actually, we could have written the induction principle manually, and we could have proven it and then used it. Using check, we can have a look at what the induction hypothesis looks like. So it's for all propositions P, if there's a nut that generates a proposition, then if that proposition holds for 0, follows if the proposition holds for the successor, then it holds for all n. Okay, we're coming back to that in a moment, just for the people who know what it is and who are interested. One more thing we need in the type universe, before we get to propositions and the interesting stuff, is polymorphic types. Again, the Haskell folks probably know that. If you use C++ templates, you know that. You can construct, types are higher order objects, and you can construct new types from old types. So this is inductive definition in the regular style, like we've seen before, for a list of booleans. We want to save booleans in a list. We have two constructors, one we call nil, and that's a boolean list on itself. And we have another constructor called cons, which is a function that takes a boolean and a list of booleans, and then returns the new list of booleans. Yeah, obvious. We have the nil constructor, we have the cons constructor, and we can actually call the cons functions, passing booleans here, here, and here, till bool nil, to construct an instance of that list. All the list programmers know, cons, how to construct lists. And of course, it's pretty bad if you keep on constructing a list type for every type of data you want to put into lists. So you can parameterize your inductive definition. You can say, I have an inductive definition that gets an argument, x of type type, and returns a type. And we can use that x as a bound variable in here in our definition. And then we see that nil actually is for all x of type type a list for that x. So if we pass that a type bool, then nil bool will produce us in nil for a boolean list, and a cons. The cons if you pass the type. So the type is passed around as an extra argument, and usually the type checker and the type inferencing makes sure you do not have to write it manually. Do not want to go into that into too much detail. Just so you have seen, we have polymorphic types. We can construct types. We can return types from functions. So check gives us a type. So if you check list, we see that list is a function that you give a type and that returns a type. And if you pass, as defined here, if you pass bool to that list, we end up with a set. So set is the type for all ordinary things like booleans, numbers, etc., etc. Of course, set itself also has a type. It is of type type. And type, again, is of type type. No, not really. There are starting indexes and type 0, type 1, type 2, just to avoid Zeno's paradoxon. You know, this sentence is false, recursive problems with, so they're using meta areas for types. So, of course, there's the interesting question, are there any other types except set? And the answer is yes, there is. And that's propositions. We've already seen propositions in our theorems. I've just used the equal sign and the propositions, figuring you see intuitively what's going on. We're now going to look into detail of how propositions work. And bear with me, because that's the second interesting part, because our dependent types consist of a type and a proposition. So types we have seen, now for propositions. 2 equals 2 is a proposition. That's a proposition. Here we see the difference between the two. So 2 equals 2 is a proposition. And BEQ nut of 2 and 2 is an expression of type bool. And the main difference is that that expression that belongs to the type set is computable. Whereas a proposition must not necessarily be computable. It might be true, it might be false, it might be undecidable, and we can still work with it. That's the interesting thing, because that's where we can apply the mathematical power and show that our puny computable function that we wrote actually adheres to some higher idea of a non-total, interesting, incomplete function that's not provable. So what can we do with propositions? We can give them a name. You already have seen theorem definitions above. You can say 2 plus 2 equals 4 gets a name. And if we do that using a theorem, we implicitly say that theorem is true. So we are now asked for a proof to show that that proposition that we gave actually is true, which of course, as we've seen, in that case is easy. You can also give some proposition a name without showing that it's true or false by just using a definition. So we see that's a proposition. We could, for instance, put a 5 here. That's still a proposition. It's a false proposition, but we do not care at that point. Theorems are always true, and we have to show that. Such definitions are not. Now you will notice an interesting fact, and that is that there's not much difference between the way sets are used in functions and the way propositions are used. So in fact, the only thing is that instead of a type here, I've written prop. And that's because propositions are part of the same universe as the other types are. They're not necessarily concrete in that you can compute them in your running program, but while you're compiling, while you're doing proofs, they exist as in the context and as goals of your proofs. Okay, so here we have given a name to a proposition. We can also define a theorem, use that name here. We can define propositions that are obviously, oh yeah, that's no longer true, I changed my code. See, that's why you do that stuff. Now that definition above is no longer a true proposition, so I cannot prove it. Have to change that back to 4. And there we go. We can define weird propositions. We can say if 2 plus 2 equals 5, then follows that 99 plus 26 equals 42. Which, by the way, is a true statement. Ex falso quod libet. We can use, we can fall back to computation for defining a proposition. We can say that computable expression equals that Boolean value, which gives us a proposition for even. So even now is a function that returns a proposition. That's interesting. So I could say even of 4, and I then get a proposition that 4 is an even number, which is either false or true. In that case, we know it's true. It's essentially, you see the similarity to how functions work while programming. I've written essentially a function that takes a natural number, and I return a proposition instead of a value. And I can do that for 3, which of course means that it's a false proposition. I can define even more complex propositions. Say that if n is an even number, then so is the successor of n. I then can do funky stuff. I can write a definition that when you pass in a proposition that maps a function that takes a natural number and returns a proposition, then returns the proposition that p is true for 0. So that it starts to boggle the mind when you think longer about it, and that's still one of the easy examples. So I have a p. My p might be even. I could take that even, which is a map from a natural number to a proposition, call true for 0 of even, and I get back the proposition that even is true for the value 0. Right? That's what I wrote there. Can come up with a definition preserved by a successor. So you take a proposition, an index proposition that maps a natural number to a proposition, and you get back the proposition that if for all n prime, if p is true for n prime, it is also true for the successor of n prime. Could be useful. We can write that a proposition is true for all numbers. So we say true for all numbers for all n, p of n. And then we can use that to define the induction principle for natural numbers. Isn't that fun? And much better readable than the other one that's auto-generated before. And as you see, we're working with